I am joined now by Arvind Kalidindi, the co-author of the 2017 JMR Paper of the Year. Congratulations. Thank you for joining us. We appreciate it.
Thank you.
So your paper details a model for making metal alloys even stronger. Before we get into how this is done, let's talk about the why. What are the benefits of stronger metals?
Yeah, so obviously we want stronger metals. In this case, we're talking about materials that have a stronger yield strength. Metals have two different kinds of strength. You have a fracture strength, the strength where if you exceed that, your metal will break. And then you have a strength where if you exceed it, your metal will bend. And oftentimes, because metals are ductile, we care about the yield strength. And so we're interested in increasing the yield strength of the materials. And the reason we are interested in that is because if you can make a higher yield strength material, that means that you can carry the same load with a smaller amount of material, which means that you can reduce the amount of cost, and you can also potentially lightweight your material. And so you can make components for things where you want fuel efficiency, like an automobile or an aircraft, with lighter components. And so as metallurgists for a long time, we've often been striving for higher yield strength materials.
Mm-hmm. Let's talk a little bit about the work that's described in your paper. What is the technique that you're presenting in that work?
Sure. So what we're interested in is one mechanism for increasing the strength of your material, which is to refine the grain size. So grain size is one of these structural features that we have control over as metallurgists, and we often try to aim for grain sizes that are small so that we can get a higher strength. It's a very well-known relationship. And so if you can get grain sizes really small, you can get really high strengths. Right now we generally have grain sizes in the micron scale regime, and what we're interested in is nanocrystalline materials, so grain sizes that are 1,000 times smaller than what we usually work with. And it's hard to process those materials because once you make grains that small, they have a very high tendency for grain growth. And so nature really wants those grains to grow, and it's very hard to process them into a bulk component. And so what my PhD has been developing and what this paper presents is a framework for designing alloys that are nanocrystalline and stable. So we can find alloy combinations that make it so that a fine grain size in the nanocrystalline regime can be stable against grain growth to higher temperatures. And that lets us process these materials. And in this particular paper, we're moving one step further even, where we can now develop phase diagrams, which are kind of the fundamental tool that material scientists use to develop new materials and process materials so that they can apply to these nanocrystalline materials, where you have new configurations and new opportunities that our statistical mechanics framework allows us to understand.
Looking down the line, what are some of the products or devices that we could see as a result of that work?
Sure. So nanocrystalline materials have a lot of applications. The end applications can be things on the structural side, like components in automobiles or airplanes where you're looking for lightweighting, or they can even be just things where you want a really high yield strength or a really high hardness. Right now, often those are things like diamond or sometimes things like depleted uranium, things that have a very high intrinsic hardness that we can maybe replace if we can make our metals that are more common higher in hardness by refining their grain size. There's also interesting applications in functional materials. There's magnetic materials and thermoelectric materials that we try to make nanocrystalline so that we can get higher magnetic coercivity, better thermoelectric figures of merits. And so nanocrystalline materials themselves are very interesting, and there's a lot of people who in their fields I think could find uses for nanocrystalline materials. My kind of contribution and my interest in this is from a purely thermodynamics perspective. It's almost like a fundamental physics approach to this, which is, can we understand these materials better so that the people who are engineers and who are going to go out and make actual products and actual parts with these, with this interesting structure, have the tools they need to select the alloy combinations that work well and figure out at what temperatures and compositions and processing conditions they can retain those nanocrystalline grain sizes. And so what I'm really trying to build here is a tool or a framework that people can apply, just like we use phase diagrams for bulk materials today, to nanocrystalline materials.
So what is the next step? What remains to be discovered in this field?
So nanocrystalline materials are relatively complex. They have grain boundaries that are complicated. And so there's definitely room for the thermodynamic models to improve by considering more of that complexity. But the models are already sufficiently complicated and sufficiently rigorous for us to start to do experiments on alloy combinations that we haven't explored before. And so I think really the next step for me personally and for our group is to try to take this framework and make it more publicly available for people to use. So over the next couple months as I finish my PhD thesis, my goal is to make a framework that is publicly available. And if there's anybody who's watching who is interested in this, please reach out to me and let me know, because we're going to try to create some sort of beta framework that we can send out to you and get a sense of whether this is useful to you, and kind of tailor it to people who are on the engineering side who are trying to make new nanocrystalline materials.
That's fantastic. Arvind Kalidindi, thank you so much. We appreciate you joining us.
Thank you.